In this episode, we'll explore the anatomy of firstly a neutron star and then the collision of two neutron stars, a kilonova. In doing so, we'll find the answer to one of the single most fundamental questions in cosmology. Why is the universe both homogeneous and isotropic? In beginning, I want to make a prediction based upon my proposed Big Bang kilonova hypothesis. That prediction being that the James Webb Telescope is going to find spiral-shaped galaxy formations dating all the way back to the time of the last scattering and recombination of the now cosmic microwave sky, some 300,000 years after the Big Bang itself. We are going to find the dark age of cosmology is not so dark as the Lambda-CDM model would have us believe. One of the most famous pictures taken by the Hubble Space Telescope was the Hubble Ultra Deep Field image, which captured the light from the most distant and earliest galaxies we have seen to date. The smallest, reddest galaxies, about 100 of them in this image, come from a time when the universe itself was only 800 million years old, meaning when the photons of light emitted from these galaxies began their journey across the intergalactic expanse of the universe itself was only 800 million years old, or rather, only 800 million years had passed since the time of the Big Bang event itself. Because the very fabric of spacetime inside our universe is constantly expanding, the wavelength of these photons are themselves also being expanded, getting longer and longer. The more time a photon spends on its journey through the intergalactic void, the greater the wavelength of that photon becomes. So a photon originally emitted in the ultraviolet end of the spectrum expands, becoming violet, then blue, becoming green, yellow, and then red. We say the photon is redshifted to the red end of the spectrum. Hence, this is the reason why the color of the earliest galaxies are red, because the wavelength of the photons from those galaxies, which have traveled for nearly 13 billion years before hitting Hubble's primary mirror, have expanded such that they are now in the red end of the spectrum. Known as redshift and denoted by Z, the amount a given photon is stretched is defined as the ratio given in equation 1, where lambda observe is the wavelength of the observed photon and lambda emit is the wavelength of the photon when it was first emitted. Cosmologists have over time developed the cosmic distance ladder, which relates the measured redshift from a given galaxy to both how far that galaxy is from us, both in space and time. The bottom line here being that light emitted by galaxies in the very early universe would have become so stretched over time that they are now only visible in the red and the invisible infrared part of the electromagnetic spectrum. The James Webb Telescope was designed and built specifically to view the red and infrared part of the spectrum, in order to see these very early galaxies, whose light is so stretched by the expansion of the universe that it is now invisible to the human eye, being in the infrared. When stretched further, infrared light becomes redshifted to the microwave wavelength of the electromagnetic spectrum. The Big Bang theory arises from the observation that an ever-expanding universe must have at some point in this distant past been a much smaller, hotter, and denser place, effectively contained as a single ball of plasma. It was only when the universe had cooled down sufficiently such that electrons could bind with protons, creating the first hydrogen atoms some 300,000 years after the Big Bang itself, did the universe go from being opaque into becoming translucent. As the universe became translucent, it was only then that the light emitted within the ball of plasma that was our entire universe began its journey across the expanse of an ever-expanding universe. Given this, the prediction was made that if true, we would expect the universe to be bathed entirely in the radiation from the time when the universe was a single hot ball of plasma. Because the universe is expanding, the light emitted from this time would have been stretched so much that it is only visible in the microwave wavelength. This, the cosmic microwave background radiation, when first detected by Wilson and Penzance, showed cosmologists that our universe was in fact born in the event known as the Big Bang. How and why this came to be in the first place can only be understood in understanding the true nature of the Philosopher's Stone, a kilonova, meaning a kilonova, the merger of two neutron stars, is one of the few places in the universe where atoms of gold are formed and scattered out into the universe, and it is from this observation that I derive my first prediction. However, alchemy, the precursor to chemistry, long sought after the ancient alchemical substance that turns base matter into gold, the mythical Philosopher's Stone. Isaac Newton himself spent his life in pursuit of the Philosopher's Stone, nature having viewed all life a fractal mirror of creation. Fractal geometry is the cosmological principle, and thus self-similar patterns repeat themselves irrespective of scale. A kilonova inside our universe arises from the merger of two neutron stars. In my Big Bang kilonova model, I begin my description in describing the merger of two neutron stars of the superverse. Thus, in order to describe a neutron star of the superverse, I look to the description physics has given us of a neutron star inside our universe, following the law of self-similarity and scale invariance. In order to understand how precious elements like silver, gold, and platinum are actually formed inside a kilonova event, we must first understand the structure of that which causes a kilonova event, namely, a neutron star. However, before I can describe a neutron star, we need to understand the alchemical nature of neutrons themselves. A neutron embedded inside a stable atomic nucleus is itself a stable particle. Outside the atomic nucleus, or in an unstable atomic nucleus, the neutron will decay into a proton, releasing an electron and a neutrino in the process. The half-life of a free neutron is around 14 seconds. Known as beta decay of a neutron, we can see the alchemical transmutation of this reaction in the radioactive decay of unstable radioactive isotopes. For example, the isotope technetium-99 has an unstable atomic nucleus with 43 protons and 56 neutrons. It has one too many neutrons. A neutron in the nucleus undergoes beta decay, releasing an electron and neutrino, with the neutron transforming into a proton. The atomic nucleus now has 44 protons and 55 neutrons, meaning the atom of technetium has transmuted into the element ruthenium. The element ruthenium being defined as having an atomic nucleus with 44 protons. So in talking about the alchemical nature of neutrons, I'm being very literal. The inverse reaction to beta decay of a neutron is called neutron capture. With neutron capture, an electron is fused with a proton such that it turns into a neutron. As we'll see, the density and pressures within a neutron star give rise to such conditions that electrons are forced into being fused with protons, turning them into neutrons in the process. The other alchemical process, which is of the greatest import in how a kilonova explosion can create gold, is by a process called the rapid neutron capture, otherwise known as the R process. The R in R process, standing for rapid, as in rapid neutron capture. There is probably not a soul on the planet who is unaware of the applicational use of the rapid neutron capture process, the R process, even if you probably never heard the term. The applicational use is in fact the atomic bomb, such as those used in 1945 on the cities of Hiroshima and Nagasaki, ending the Second World War. Fission inside an atomic warhead is the rapid neutron capture process in full effect. The warhead is composed of the isotope uranium-235. The atomic nucleus of uranium-235, when hit with a free neutron, becomes unstable, and the atomic nuclei splits into krypton-89 and barium-144. But in addition, the splitting of the uranium-236 nuclei releases 3 free neutrons at very high speeds. These 3 neutrons in turn collide with 3 more atomic nuclei of uranium-235, which in turn splits, releasing 9 free neutrons in the process. These 9 neutrons collide with 9 more uranium-235 nuclei, which split, releasing 27 free neutrons. 27 becomes 81, 81 becomes 243, 243 becomes 729, and so on, tripling the number of neutrons each time. This chain reaction runs out of control, and the conversion of atomic mass into energy, as described by Einstein's most famous equation, E equals mc squared, is released, creating the nuclear explosion. It is the production of free neutrons in a chain reaction, which in turn slam into other atomic nuclei, that in turn splits, producing even more free neutrons, which is the rapid neutron capture process, or R process. This process, or rapid neutron capture, is effectively responsible for the creation of all elements heavier than iron. The reason is that the fusion of all elements lighter than iron all release energy, so when a star comes to the end of its life, having fused all lighter elements into heavier ones, then when iron is fused, it consumes energy, as opposed to releasing it. This consumption of energy causes a star's core to collapse in itself, triggering a core collapse supernova. The fusion of iron inside the collapsing core creates an environment rich in free neutrons that in turn are absorbed by the surrounding atomic nuclei. It is the absorption of these free neutrons, coupled with their fusion of heavier atomic nuclei in the milliseconds of the collapsing core, that was thought to be the forge in which all elements heavier than iron came into being. I say thought in the past tense, as advances in particle physics have shown that heavier elements are not only forged inside supernovae and hypernovae. Silver, gold, and platinum have also been shown to come from the R process in the heart of a kilonova, the true philosopher's stone. But before we can get there, we need to understand the structure and anatomy of that other product which is born in the heart of a hypernova, that being a neutron star. In truth, there is much debate and speculation about the nature of matter inside a neutron star. Born from the core collapse of a hypernova, the state of matter inside a neutron star is described as being a form of matter known as a degenerate form of matter composed primarily of neutrons. Degenerate matter is effectively a form of matter where every bit of space within the volume of a neutron star is occupied by a neutron. Degenerate matter arises from Pauli's exclusion principle, which states that no two fermions, particles with half-integer spin, can occupy the same quantum state. Electrons, protons, and neutrons are all fermions, whose spin is a half-integer. As a given neutron within the neutron star decays, the resultant electron is unable to find an unoccupied quantum state, and thus the neutron is unable to decay. Atoms, as we know them, are mostly filled with empty space. The amount of space occupied by the atomic particles in an atom of hydrogen containing a proton and an electron is only 1/1000th of the total volume. The other 99.99999999996% of the volume of the hydrogen atom is totally unoccupied free space. So when we talk about degenerate forms of matter, we are talking about matter whose every bit of volume has been packed with particles. A teaspoon of electron degenerate matter, such as that found in a white dwarf, would weigh around 5 tons. Even heavier, a teaspoon of neutron degenerate matter, such as that found in a neutron star, would weigh 5 billion tons, the weight of Mount Everest inside a single cube of sugar. Probably the most basic description of a neutron star would be to describe it as being like a crystal lattice structure, where every position on the crystal lattice is occupied by a neutron. Crystal lattice structures in nature, such as table salt or quartz, form cubic or hexagonal lattice structures. Each atom in the crystal lattice is bound to another through an electron covalent bond. As the geometry of a crystal lattice structure is one of the most efficient arrangements by which to order the packing of neutrons, such that there is a minimal redundant free space, is what gives rise to this very basic description of a neutron star. As the mass energy density of any given neutron in the universe is the same, each being 939.6 mega-electron volts over c squared, then each neutron inside a given neutron star also has the same mass energy density. Given the regular geometric shape of a crystallized lattice, we have in effect a perfectly homogeneous material where each neutron in said lattice has the exact same quantity of mass. In other words, the neutron star can be viewed as a compact astrophysical body composed of a perfectly homogeneous form of matter. The other equally important thing to note about a crystal lattice structure is that it has the same repeating unit pattern of geometry in all places, regardless of direction. For example, a tetrahedron is a pyramid whose 4 faces are each composed of 4 equilateral triangles. With the tetrahedron as our basic repeating unit, we can build a crystal lattice known as a tetrahedral octahedral honeycomb. Another example is a cube whose 6 faces are a regular square. The crystal lattice formed is called a cubic crystal system, or to give it its other name, an isometric crystal system. Effectively, the matter inside a neutron star can be described as the most perfectly homogeneous and isotropic form of matter. In applying the causation of the Big Bang being due to a kilonova event inside the superverse, we immediately answer one of the most fundamental questions in physics, namely, why is the universe homogeneous and isotropic? Or mostly isotropic, as we'll get onto the large-scale anisotropies later. The alternative, however, the Lambda-CDM model, states that as its cosmological principle, the universe is both homogeneous and isotropic. It doesn't even attempt to answer this question, but rather assumes it. Since figuring this out, I've gone on and developed a certain kind of dance that I call the winner's boogie, in being able to answer this single most fundamental question in all of physics, and we haven't even got on to talking about mass Cooper pairs, which in fact we need to talk about because they give rise to the generation of the neutron star's colossal magnetic field. From a symbolical point of view, A neutron star can be described as a spherical body with a surface, and like any other astrophysical body, it has a core. This core, as we'll discuss, is distinct from the crystallized crust and mantle. The crystallized crust are represented in the Platonic shapes, a triangle for a tetrahedral lattice and square for an isometric cubic lattice. Together, they form the alchemical symbol of the philosopher's stone. Describing a neutron star as a uniform crystal lattice does as a beginning, but we really need a more detailed description in order to understand the initial conditions that gave rise to the Big Bang kilonova itself. A much more accurate description would be to view it as a rocky planet such as Earth. That is, to view it as having both an atmosphere surrounding a solid crust, wherein there is a mantle surrounding the outer and inner cores. Imagine now being an astronaut, traveling towards a neutron star upon which we will first descend, before then traveling on downwards to the core. The first thing we'll encounter as we approach a neutron star is its magnetic field, coupled with how its extreme density causes the fabric of spacetime to warp. The strength of a neutron star's magnetic field is between 100 million and 1 quadrillion times stronger than our own Earth's magnetic field. Effectively, a neutron star has one of the most powerful electromagnetic fields in the entire universe. Magnetars, a type of neutron star, are considered to have the most powerful. Because of their strength, atoms as we know them become deformed, and where matter and antimatter are born in the vacuum of space. It is here we get a key insight into the fractal nature of the cosmos and the embodiment of the Big Bang kilonova hypothesis cosmological principle. The Schwinger limit at a value of 4.41 trillion Tesla is the strength at which the equations describing quantum electrodynamics and the electromagnetic field become non-linear. An electromagnetic field whose strength is below the Schwinger limit is described in a linear fashion. A field such as the one around a neutron star or a black hole, whose strength is above this, is described in a non-linear fashion. As fractals and chaos arise from non-linear dynamics in mathematics, coupled with how I place the birth of a black hole at the heart of my Big Bang model, seeing this insight is key, I feel. It gives a physical and mathematical reason derived from quantum electrodynamics in drawing a parallel between black holes and fractal geometry. One such effect arising from the nonlinear dynamics of the electromagnetic field is the sudden creation of positron and electron pairs from empty space. In a vacuum, the classical Maxwell equations are perfectly linear differential equations, which implies, by the superposition principle, that the sum of any two solutions to Maxwell's equations is itself a solution to Maxwell's equations. In other words, it is linear. For example, two intersecting beams of light should simply pass right through each other. The luminosity of the intersecting beams is found by adding the luminosity of each of the beams together. But in considering the collision of two photons in quantum electrodynamics in a field whose strength is greater than the Schwinger limit, the nonlinear dynamics of the electromagnetic field leads to the creation of positron and electron pairs, known as pair production. The collision of two gamma-ray photons produces an electron and along with its antiparticle, the positron. As the very creation of matter is a fundamental requirement of any Big Bang model, we find this requirement is fulfilled arising from the nonlinear dynamics of a sufficiently strong enough electromagnetic field, the measure of what is sufficient being the Schwinger limit. The other effect arising from the sheer mass-energy density of a neutron star is the warping of spacetime. Mountains as high as 10 centimeters exist upon the surface of the neutron star. Now, these molehill-sized mountains would effectively weigh around 70 times the weight of Mount Everest. It is reckoned that due to their extreme mass-energy density, these molehill-sized mountains upon the neutron star's surface warp the very fabric of spacetime to such a degree that gravitational waves ripple out from the star as it rotates. These gravitational waves are in addition to the extreme warping of spacetime coming from the neutron star as a whole. By knowing the frequency of rotation for a given neutron star, physicists at LIGO hope to try and detect these gravitational waves, or ripples rather, whose frequencies are expected to be in sync with the rotational frequency of the given star. So, in reality, as an astronaut traveling towards a neutron star, the atoms making up your body will effectively be elongated and spaghettified both by the electromagnetic field and by the relativistic warping of spacetime. Though before this happens, the very strength of the electromagnetic field would stop the functional interaction of enzymes like hemoglobin, and we would be dead before witnessing such a fate. But in our imagination, we continue our journey towards the surface of our neutron star. As we approach the neutron star, we will see a haze-like shimmer coming from the atmosphere surrounding the neutron star itself. But unlike the atmosphere of Earth, this atmosphere is effectively an electron-degenerate form of plasma. Electron-degenerate matter is the form of matter mostly found in the neutron star's lighter cousin, a white dwarf, formed by the core collapse of a star like our own Sun. In this electron-degenerate plasma are the atomic nuclei of that matter which has fallen onto the neutron star since its birth, so mostly hydrogen and helium nuclei. In between the nuclei is a thick fluidic soup of electrons, where every space or quantum state rather is occupied by an electron. Pauli's exclusion principle states that two identical half-integer spin particles, fermions, cannot simultaneously occupy the same quantum state, meaning that no two electrons, which are fermions, having half-integer spin, can occupy the same electron orbital at the same time. But more generally, this principle extends to both protons and neutrons, in that neither can occupy the same quantum state, given that they too are half-integer spin particles. The result of Pauli's exclusion principle is that an emergent pressure against further compression arises. It is this pressure that stops the white dwarf and neutron star from undergoing total gravitational collapse, unlike a black hole. As we travel down through the crust of a neutron star, we will see how this electron-degenerate matter turns into a neutron-degenerate form of matter. Inside the atmosphere of a neutron star, we have an electron-degenerate plasma, an electron soup whose croutons are the atomic nuclei of matter captured by the neutron star's gravitational attraction. As the most common free elements in the galaxy are hydrogen and helium, then the vast majority of nuclei in the electron-degenerate atmosphere will most likely be hydrogen and helium nuclei. Also, because of the neutron star's massive gravitational attraction, this atmosphere rises to the astronomical height of 1 meter. Or rather, if you were to stand upon the surface of a neutron star, the atmosphere will only come up to your waist. Your head will be in the free vacuum of space. The actual surface of the neutron star is itself an electron-degenerate plasma which has frozen into a crystalline lattice. The positive like charges of the atomic nuclei within the electron-degenerate plasma repel one another, but given that there is nowhere for a given atomic nuclei to move to, the net result is that a crystalline lattice arises. The atomic nuclei form the nodes of the lattice, with each nuclei being equally repelled by the surrounding nuclei. Here in the crust, we begin to see the alchemical nucleosynthesis process that creates all forms of rare and exotic elements and isotopes. This alchemical process is driven by both the beta decay of neutrons and the neutron capture processes. As we discussed, an unstable neutron will undergo beta decay, turning into a proton while ejecting an electron. Neutron capture is the inverse reaction, which sees an electron being forced to fuse with a proton into becoming a neutron. An unstable neutron undergoes beta decay inside an atomic nucleus, which in turn becomes a proton while ejecting an electron. As each element is defined by the number of protons inside their nuclei, the addition of a new proton inside the nuclei effectively transmutes the atomic nucleus into becoming a new element. Given that each element in the periodic table is defined by the number of protons in the nucleus, the addition of a new proton from the beta decay of a neutron effectively transmutes the nucleus into being the next element in the periodic table. So, iridium with 77 protons can decay into platinum with 78 protons, and then into gold with 79 protons. In inverse, the neutron capture process forces an electron into a proton, such that it creates a neutron. Thus mercury, with 80 protons, undergoes neutron capture, creating a gold nuclei with its 79 protons. The deeper we go into the crust, the greater the pressure applied from the weight above does become. Just like rock upon Earth, the deeper we go down into the crust, the greater the pressure becomes coming from the weight of the rock overhead. But rather than rock, the pressure from overhead comes from the weight of the electron-degenerate matter that is above. This pressure from overhead forces electrons into protons becoming neutrons, thus driving a very gradual neutron capture process. Meaning, the deeper we go into the crust, the heavier and more neutron-rich the atomic nuclei are going to become. Initially, the atomic nuclei entrapped in the crystallized electron-degenerate crust were those nuclei created by the rapid neutron capture process that happened as the collapsing core of the dying star gave birth to the neutron star itself. The lighter nuclei, such as iron, are most abundant at the surface, with heavier nuclei lying deeper down inside the crust. With reference to Wolf, Beck and Blom paper Plumbing Neutron Stars to New Depths with the binding energy of exotic nuclide zinc-82, we see this illustrated in figure 1. Iron with 26 protons is close to the surface. This is followed by nickel with 28 protons, then krypton with 36 protons, followed by selenium and ruthenium. The rate of neutron capture increases the deeper we go, creating heavier and heavier isotopes of a given element as the respective nuclei gains more and more neutrons. An isotope of an element is defined by the number of neutrons within the nucleus. The deeper we go, the more the neutron capture process dominates, and thus isotopes containing more and more neutrons are formed. This can be seen in the case of nickel with 28 protons, where nuclei near the surface have an atomic weight of 62, implying its nucleus has 34 neutrons. Further down inside the crust we find nickel with an atomic weight of 80, implying its nucleus has 52 neutrons. The deeper we go, the greater the pressure from overhead. The electrons of the electron-degenerate matter are forced to be merged with protons turning into neutrons. By this point, we are about half a kilometer deep. The further down we go, the more free neutrons come to occupy the spaces between the atomic nuclei as opposed to electrons. Thus, the electron-degenerate matter turns into a neutron-degenerate form of matter from which the mantle is thus composed. From this point in, speculation as opposed to experimentation reigns. We are beyond the current limit of nuclear experimentation and into the realm of theoretical. Here the density is about 1 trillion times denser than matter here on Earth. Inside the core we have nuclear pasta, the first layer being of the spaghetti variety. In effect, the previously separate atomic nuclei have merged into forming long chains of atomic spaghetti. It is the balling up and entanglement of the spaghetti that leads to imperfections which pushes upwards, deforming the mantle and crust, such that the mountain-sized molehills upon the surface are formed. Alternatively, like the frozen plasma of the atmosphere, which is itself the surface of the neutron star, the neutron degenerate plasma is itself frozen, thus forming a single isotropic and homogeneous crystallized lattice mass of neutrons. By trying to detect whether a neutron star emits gravitational waves arising from these mountain-sized molehills is the way these two alternatives can be tested. Further down in the past model, these long chains are further compressed into layers and then into a crystallized mass. This is probably the single strongest material in the entire universe, with a tensile strength quintillion times stronger than steel. The massive strength of this material, coming from the neutron degenerate pressure, holds a neutron star up from total gravitational collapse down into a black hole. The density down here is 200 trillion times the density of anything found or here on Earth. It is down here towards the inner core we finally arrive at something I have spent the last couple of years looking for: the Cooper pair, named after Leon Cooper, who with Bardeen and Schleifer discovered the quantum phenomenon of paired fermions, such as the electron and neutron, that makes matter both a superconductor and superfluid. The formation of a Cooper pairing is a quantum effect, but in a simplified classical explanation, let us consider the atomic lattice of a metal. An electron in a metal normally behaves as a free particle. The electron is repelled from other electrons due to their negative charge, but it also attracts the positive ions that make up the rigid lattice of the metal. This attraction distorts the ion lattice, moving the ion slightly towards the electron, increasing the positive charge density of the lattice in that vicinity. This positive charge can attract other electrons. At long distance, this attraction between electrons due to the displaced ions can overcome the electrons' repulsion due to their negative charge and cause them to pair up. It is this forming of paired electrons, or more generally fermions, that is called a Cooper pair. This pairing is seen in superconductors, material whose electrical resistance is zero, and it is because of this pairing that a material becomes a superconductor. A metal can become a superconductor when it drops below a critical temperature. As the temperature cools down, the rate and magnitude at which the atomic nuclei shake within the metallic lattice decreases. As the rate decreases, the rate at which electrons randomly bounce or repel each other, in turn, decreases, thus giving more time for the lattice to deform such that ions are attracted to a given electron, which in turn attracts more electrons. Below the critical temperature, the long-distance attraction between electrons comes into effect as all the electrons pair up with one another into forming Cooper pairs. When half-integer spin particles, fermions, such as the electron, neutron, and proton bond together, forming these Cooper pairs, the very nature of the particle changes. They turn into bosons, with either a spin of 1 like the photon, or a spin of 0 like the Higgs particle, meaning they are no longer behaving like particles on an atom, but rather as a particle that conveys force. For example, the photon with a spin of 1 conveys force upon the electromagnetic field. The movement of electrons through the metal now is unidirectional and without resistance, coming from the organization of electrons into Cooper pairs. It is this quantum mechanical behavior, more formally known as the electron-phonon interaction of paired electrons at long distance, that effectively make the metal a superconductor. Ultimately, Quantum mechanics tells us that the physical electron itself is a probability wave with no hidden variables. The interpretation I apply in my reasoning, derived from relativity, comes from seeing the very fundamental way in which a dimension of space can become time, and vice versa, a temporal dimension can become a spatial dimension. This interpretation is derived from both special and general relativity in considering superluminal travel in special, and in the general by the flow of spacetime below the event horizon of a black hole. In applying this interpretation of relativity to quantum mechanics, I followed the golden rule that fractal geometry is a cosmological principle and that self-similar patterns repeat themselves irrespective of scale by the law of self-similarity, as entangled particles are bridged by wormholes. Or rather, the ER equals EPR conjecture, proven by Leonard Susskind and Juan Maldacena in 2013, is now backed up by experimental evidence as demonstrated on Google's quantum sycamore chip. In applying the mathematical law of scale invariance to our map showing the inside of a rotational black hole, as described by the Kerr metric, I apply this map directly in understanding the anatomical structure of a pair of entangled particles. In describing a field, be it gravitational or the electromagnetic, I imply this interpretation of dimensional role swapping between entrapped temporal and spatial geodesics. The surface of a given field being described as an entrapped or enclosed geodesic, wherein time is three-dimensional and space is unidimensional, or rather, the one-dimensional spatial quantum wormhole through the electromagnetic field within Google's quantum sycamore chip is equivalent to two entangled black holes whose wormhole is through the gravitational field. The gravitational field being the equivalent of the electromagnetic field of the superverse as dark energy imbues solidity. With this in mind, I describe a single fermionic quantum probability wave as being a closed geodesic volume of entrapped spacetime. Usually, the wavelength of a given probability wave is smaller than the scale of an atom, but as the temperature drops down towards absolute zero, the wavelength of the probability wave spreads out. So in the case of the formation of Cooper pair electrons, the wavelength of each electron's probability wave increases and spreads out. It spreads out to the point where the two probability waves join together and become a single unitary wave of probability whose very nature has changed. The two probability waves of the electron have a half-spin integer, meaning that neither can coexist in the same volume of space. But as a single unitary wave of probability, it now has either no spin like the Higgs boson or the photon with spin 1, meaning that two Cooper paired electrons or Cooper paired neutrons can coexist in the same volume of space. Given both how we see the formation of Cooper pair electrons in superconductors and superfluids, coupled both with the observation that magnetars are neutron stars and how fermions become bosons, gives rise to this description of the neutron star's core. Although Cooper pairing in human experimentation is related to temperature, so too is it related to the pressure. So even though the core of a neutron star may be one of the hottest places in the universe, it is one imprisoned by a nearly perfectly spherical mantle whose weight and strength contains this quantum pressure cooker. Of course, in considering an asymmetrical mantle and core, we have this simulation of a young, unstable neutron star being forged in the milliseconds preceding core collapse of a given star, shattering and reforming into a more symmetrical circular shape. But in talking about condensed matter physics, let us for the moment continue down the temperature scale. Individual atoms can themselves be described as a single probability wave. As the temperature drops, the probability wave that is the physical atom itself also spreads out. Then, in the same manner as to how Cooper pair electrons form, the very atoms merge together, such that they act as a single unitary wave function of entrapped three-dimensional possibility. Here, a billionth of a degree above absolute zero, groups of atoms merge together into becoming a Bose-Einstein condensate. With a superfluid like liquid helium, this behavior of Cooper pairing is also seen, particularly in the case of helium-3. Like a superconductor, in that below a critical temperature and pressure, the atoms in the fluid spread out into forming Cooper pairs, which causes them to flow with zero resistance or viscosity. Viscosity being the equivalent to electrical resistance in how the fluid flows is suddenly gone as the atoms form pairs and move in unison together. If there is one thing that lights up my inner geek, it is experiments of Bose-Einstein condensates in rotation, particularly ever since I first laid eyes upon Martin Tajman's paper describing his experiment. The importance of Tajman's experiment is that it potentially shows a man-made experiment, which I would love to see reproduced, in which an effect known as frame dragging may be happening. Now, frame dragging is an effect arising from rotation of a body within the context of general relativity, or to put it bluntly, that's potentially frame dragging in a lab, something many physicists would say is impossible. To put this into context, to test the very idea of frame dragging itself, the size of the required lab was the entire Earth itself, and whose effect is so weak that it took physicists like Francis Everett a lifetime to produce one of the world's most sensitive experiments in the form of Gravity Probe B. As a curious note in making this film, I do wonder why all the film footage of liquid helium is grainy, black and white footage. This footage talks about the effect of rotational helium, very rare footage and none in color. This to me stinks, and I think I smell a skunk in the works. Just saying as someone who grew up around test pilots, but if anything, a photo says 1,000 words. This photo is showing the gaseous formation of sodium atoms as a Bose-Einstein condensate in rotation. The temperature of the gas is only a billionth of a degree above absolute zero. The quantum probability wave, which is the physical sodium atom, has effectively spread out to such a degree that it can be photographed with a camera looking down at a microscope. For scale, the diameter of the photo is 1 millimeter. So what you are seeing in this photo is quantum mechanics. At higher temperatures, the length of the quantum wave, that is the physical atom itself, is confined to being inside the atom itself. So quantum mechanical effects are not usually seen at scales larger than the atom. But because the temperature is only a billionth of a degree, the quantum wave, and hence its wavelength, have spread out. Again, for scale, the photo itself has a diameter of 1 millimeter. This is a photo of the quantum world itself. My hat is off to Wolfgang Ketterl and his team at MIT. That is a photo showing quantum mechanics in action. Understand that quantum mechanics describes the world at the atomic and subatomic scale. Above that scale, we describe the world in terms of classical Newtonian physics. So the ability to see into that world by causing the wave function to spread out really blows my mind. This is a photo of that which physicists once thought impossible to ever see, the quantum world. The part that gets my full and undivided attention is the hexagonal flower of life pattern. I cannot even put into words the psychic strain that I have felt in understanding the true divinity of this one particular symbol from sacred geometry. Apollo be praised! But for the moment, staying inside the realm of scientific discord, this is a photo of sodium atoms being rotated, or rather, it is a superfluid in rotation. A normal fluid, when forced to rotate after initial transient, acts as a rigid body, where the velocity smoothly increases from the center to the edge. However, this smooth variation is impossible for particles in a single quantum state, as the sodium atoms in the photograph are. Because of this quantization, the flow of the superfluid develops a hexagonal formation with quantum vortices at each of the intersections. The flow of the fluid is essentially trapped or confined to the spaces between the hexagonally arranged sodium atoms. Types of classical vortices in nature include whirlpools and tornadoes. The flow of the fluid is around a central point which draws the fluid in and downwards. A vortex ring, also called a toroidal vortex, is a torus-shaped vortex in a fluid. That is, a region where the fluid mostly spins around an imaginary axis line that forms a closed loop. The half-integer spin of fermions is best described by Dirac's belt trick, but in visualizing a particle with these vortices, pictured herein, it is the closest description I have to what a quantum vortex looks like. To see this visualization, this experiment shows the collision of two vortex rings with each annihilating the other. It's how I imagine what pair annihilation actually looks like. The flow of the superfluid is confined to the vacuum space between the hexagonal spaces between the sodium atoms. That flow is the quantized angular momentum spin of vortex rings, but like a vortex, it pulls the fabric of reality down somewhere and to where we'll discuss in a future episode in our journey down to 0 point. For the moment, in looking at the sodium atoms as a rotational superfluid, these quantum vortices are arranged in a hexagonal formation. Having now explained one of the photos, we can discuss the difference between each of them. The difference is the rate of rotation. The higher the rate of rotation, the greater the density or the number of vortices. The first photo shows 16 vortices, then the next photo shows 32, then the next 80, followed by 130 vortices. With each step, the rate of fluid rotation becomes higher and higher, as the number of quantum vortices increases in an integer-stepped manner. This is what is meant by quantized flow, this integer-stepped increase in the number of vortex rings in the vacuum of space. But what has all this got to do with the core of a neutron star? Everything, as without explaining Cooper pairs, superconductivity, quantum vortices, and superfluidity, we are unable to talk about the core of a neutron star. Or I could give it a very basic description. Inside the core, some think, the structural integrity of the neutron breaks down. The quarks and gluons that make up the mass of the neutron are no longer a single particle. Effectively, this gives rise to a form of matter called a quark-gluon plasma. The only other place in the universe where matter existed as a quark-gluon plasma is in the first few seconds preceding the Big Bang, when all the matter in the universe was a quark-gluon plasma. So if there is an answer to where did the quark-gluon plasma that was the early universe come from, in describing the collision of two neutron stars, a kilonova, as the primary cause, then we have answer to that question. from the core of the two superneutron stars. That's the beauty of the Big Bang Kilonova hypothesis. Simple answers to impossible questions. Though, the collision of two neutron stars grinding each other down, turning the whole mass into a quark-gluon plasma, adds to that which already exists in the core, as we'll see later. But a more detailed description of a neutron star's core would be to describe it as being both a superconductor and a superfluid whose rate of rotation is so high, approaching the speed of light, that the magnetic field it generates is one of the strongest in the universe. The higher the rate of rotation, the greater the magnetic field generated by this dynamo. A magnetar star, which generates the strongest field in the universe, is a neutron star whose superfluidic core is spinning so fast that it powers the energy within these fields. The reason the core has become both a superfluid and a superconductor is that the neutrons have bonded, forming Cooper pairs. The idea is that the pressure upon the crystallized lattice of neutrons becomes so great from above that above a critical pressure the neutrons are forced into arranging themselves as Cooper pairs. Being a Cooper pair, the two neutrons stop behaving as two half-integer spin particles. The two neutrons, when bound together, now behaves as a boson particle, which is no longer subject to Pauli's exclusion principle. Just as a Bose-Einstein condensate is created when dropping below a critical temperature, so too does the core of the neutron star become such a condensate above a critical pressure. Pauli's exclusion principle forbids any two half-integer spin particles from occupying the same quantum state. The pairing of half-integer spin neutrons into Cooper pairs transforms the two fermions into a single boson which can occupy the same quantum state. Thus the core can fit a greater number of neutrons than the crystallized lattice above because Cooper paired neutrons acting as a single boson can occupy the same quantum state as other Cooper paired neutrons. The state of the crystallized lattice suddenly gives way to the spinning superfluid, which cumulatively is best described as being a quark-gluon plasma. Being a superfluid in rotation means the flow of the fluid itself is quantized, such that it generates very powerful quantum vortices within the core. Glitches in the regularity of a pulsar, a neutron star as observed from Earth, are theorized to be caused by the generation of these quantum vortices. One extremely interesting idea is the idea that these quantum vortices are formed inside the core of a black hole. The idea extends from quantum gravity, where the particle gravity, the graviton, is a spin 2 boson, behaving like a Bose-Einstein condensate or a neutron star's core. The spinning ringularity itself acts in a similar manner in being both a superconductor and a superfluid. Effectively, the ringularity of a rotating black hole could be described theoretically as being a Bose-Einstein condensate of graviton particles. Thus, the ringularity inside the black hole generates these quantum vortices which are thought to act in a similar manner, similar to how sunspots appear. A sunspot is an area upon our star's surface that is caused by the intense concentration of magnetic field lines within a local area. These intense magnetic field lines are generated by the rotation of the sun's core. These intense magnetic field lines inhibits the convection of plasma, causing the surface plasma to cool, which in turn decreases the intensity of light emitted in that local area. Thus, a sunspot is seen as a dark spot upon the sun's surface. But in the case of a black hole, and because of the quantum nature of these vortices, the intense magnetic field line running through the center of the vortex can possibly escape the event horizon, or rather, it acts as a sunspot upon the event horizon of the black hole. This effect, via quantum mechanics, would then be imprinted upon the magnetic field surrounding the black hole. As the Event Horizon Telescope can now picture the actual magnetic field lines of a black hole, it opens a window into being able to test such an idea. This is what makes this idea so brilliant, in that it actually provides a window into the black hole that can be tested through direct observation. But not to be outdone, we will actually look at the direct effect of matter that has actually been pulled through the singularity of a black hole later on in this episode. The inner core of a neutron star, I feel, is simply a quark-gluon plasma surrounded by the superconducting superfluid of the outer core. Such is the weight and pressure that the neutrons have lost all integrity and cohesion, that they have become unbound within the inner core. The quarks and the gluons that make up the mass of the neutron are freed, and the resultant plasma soup is a quark-gluon plasma, the same state of matter that the entire universe was in following the first few seconds preceding the Big Bang event itself. Having now fully described the structure of a neutron star, are we able to describe the actual Philosopher's Stone itself, the kilonova event itself? A kilonova arises from the collision of two neutron stars with one another. Attracted by the gravitational pull upon the other, the two neutron stars orbit about each other. With each full rotation, the two stars move closer to one another as they progressively spiral in towards each other. Because of the extreme density and weight of each of the two neutron stars, the metric fabric of spacetime is warped in such a manner that gravitational waves are formed, which in turn ripple out across the fabric of the universe. As the two stars come to be closer and closer together, the greater the distortion in the fabric of spacetime becomes. Coupled to this is that the frequency of each orbital rotation about the other increases. The cumulative result is that both the magnitude and frequency of the gravitational waves spiraling out from the two stars continually increases until the two stars actually collide. Gravitational observatories, like LIGO, detect the gravitational waves being emitted from our two neutron stars orbiting the other. A gravitational observatory works using a device known as a laser interferometer, which acts by bouncing a laser back and forth between two concave mirrors in such a way a regular interference pattern builds up. When the fabric of spacetime is warped, such as when the gravitational wave passes through the laser interferometer, the resultant warping changes the path traveled by the laser, which is then seen as changes in the resultant interference pattern. By detecting these changes in the interference pattern, physicists are able to detect the presence of gravitational waves while also being able to measure the wave's magnitude and frequency. The LIGO observatories employ two laser interferometers, each one built at a 90-degree angle to the other. This is to allow the observatory to find out from which direction the gravitational wave is traveling from. Looking down, if the gravitational wave traveled in a vertical direction from bottom to top, then the metric of spacetime would oscillate in the vertical direction. This compression of spacetime in the vertical affects the flight time of the vertical laser, which in turn is detected as a change in the interference pattern of the recombined lasers at the detector. As the wave is orthogonal to the horizontal, then no change is seen in the flight time of the horizontal laser. Vice versa, a wave traveling from left to right would be seen by the horizontal interferometer while unseen by the vertical interferometer. for a wave in between, then both interferometers would see the wave, and finding its direction would be a simple matter of trigonometry. Such is the sensitivity of these LIGO observatories that they can detect the warping of space-time to within a billionth of a millimeter. To ensure a valid result, as opposed to an invalid one, such as might happen when a truck drives within 10 miles of an observatory, and to cover blind spots, a number of gravitational observatories have or are currently being built around the world. When two or more observatories record the same event, then it is considered a valid result, having been reproduced. This was seen in the case of GW 170817, the first binary neutron star merger ever seen and recorded in 2017. Both the Hanford and Livingston LIGO observatories in the US detected the Kilonova event, but the Virgo observatory did not. Using this information, the LIGO astronomers triangulated the potential source of the Kilonova event to two patches of sky in the southern hemisphere. Astronomers using optical telescopes have for a long time been trying to develop techniques which allow them to capture the light of a nova as it actually explodes. The problem is that novas are very short events. There is the initial explosion, which lights up the area, meaning a supernova in a galaxy will for a short moment be brighter than the galaxy itself. This explosion of light, over the course of the next few days, cools down and fades. So the quicker astronomers are able to detect the location of a nova, the better the observations are going to be, as many telescopes rapidly home in on the area where the nova is about to or is occurring. Because of a nova's short but bright time span, such astrophysical events are called transient events. Towards this end, astronomers launched specialized satellite missions, such as the Swift and Fermi telescope, which detect light in the X and gamma ray end of the electromagnetic spectrum. Shortly after LIGO had seen the gravitational waves from GW 170817, the Fermi telescope detected a gamma ray burst event. 15 hours later, Swift detected a short gamma ray burst coming from around the same region of the southern sky, narrowing the search window even further. Marshaled, nearly every available telescope swung their sights upon this window, as the source of the kilonova was identified to be coming from the galaxy NGC 4993. Thus, we saw our first kilonova caused by the merger of two neutron stars. This footage here, taken by the Hubble Space Telescope over the course of 6 days, shows the light from this kilonova. As a side note, can the ESA come up with a new space telescope and call it the Lemaitre Space Telescope? I mean, did you ever hear the tale of the primeval atom?
Of course, one part of the rays could have escaped this process of condensation. And there we have perhaps a different element, maybe in the theory of the primeval atom, that a part of these rays have escaped, hardly containing any hydrogen, and that one might find these rays inside the cosmic radiation.
You have now, as that is exactly what a neutron star is. After all, it was Lemaitre and not Hubble who discovered Hubble's law. It was Lemaitre who first showed Einstein the consequence of applying his theory of general relativity, which described an expanding universe. Einstein, who believed in the long-established steady-state model, initially messed up his own calculations to disprove Lemaitre's idea. Friedman, who was better at the subtleties of tensor calculus, showed Einstein his mistake, which then caused Einstein to introduce the lambda into his field equation. Einstein later took it out, calling it his greatest mistake, after Hubble finally convinced him that the observational data showed Lemaitre was right, and that we live in an expanding universe. Now, how and why this came to be, Lemaitre attempted to answer this by way of his idea of the primeval atom. That was before Hoyle coined the term Big Bang. Lemaitre was a genius, and I might as well call my hypothesis the twin primeval atom hypothesis. Though being honest, I just did it for the lulz. But to appease my ego, I do have this funny notion that interstellar empires will be named after me itself. What really surprised scientists in capturing the light and afterglow of a kilonova was its spectral pattern, or absorption lines. The spectral absorption lines showed the presence of precious metals such as gold and platinum and other rare heavy elements, meaning that a kilonova is actually responsible for the creation of gold. Prior to this, it was believed that core collapse supernovae were responsible for the creation of gold, but since then, nuclear physicists have recalculated the numbers and determined that gold is actually formed in the heart of a kilonova and a hypernova. Without them, there would be no gold or any other element heavier than iron in the entire universe. So when I say a kilonova event is the Philosopher's Stone, I am being very literal about that, and this fact is not one of mere theoretical calculation. No, it is one of fact, borne out by direct observational evidence, namely the spectral light of the kilonova event itself. In order to understand the Big Bang kilonova hypothesis, let us study the anatomy of a kilonova explosion and the subsequent black hole it gives birth to. A kilonova, the collision between two neutron stars, starts with the gravitational pull of one upon the other. This gravitational attraction upon the other causes each of the two neutron stars to form a circular orbit about the other. However, this circular orbit is not stable, the gravitational attractive force between the two bodies being greater than the outward centrifugal force causes them to be pulled in towards one another. Thus they spiral in towards one another, with each complete orbit becoming shorter and shorter as their angular momentum continues to be accelerated. For clarity of description, we label our two neutron stars as both A and B. The closer one is to a given neutron star, the greater its gravitational force of attraction becomes. Thus, the closer a given neutron star is to the other, the greater the gravitational force that is exerted upon the other. Thinking about the surface of star A, one side of star A's surface is pointing towards B, and hence closer to B. Vice versa, the other half of star A's surface is pointing away from star B, meaning half the surface of A is closer to B than the other half at any given moment in time. Hence, the surface of A that is closer to B experiences a greater pull towards B relative to the far side surface of A, upon which a lesser force is exerted, being further away from B. Because the mass of a neutron star is so extreme, this difference in the gravitational force of B being exerted upon the surface of A causes the spherical neutron star to deform into becoming elongated and egg-shaped. Effectively, The closer the surface of one star is to the surface of the other, the greater the pull, such that the spherical star is stretched out, elongated, into becoming egg-shaped. When stretched out further, the star becomes more pear-shaped. Now the neutron stars themselves each have their own axis of rotation, about which the spherical body rotates. But as this body is stretched out to look like an egg, the surface being stretched is constantly changing because of the body's own rotation. So for a fixed point on the equator, it will be stretched as the body of A rotates such that our fixed point moves closer to B. It will then reach the point of greatest exertion when the distance to B is at its minimum. For the next half rotation of A, our point moves away from B, causing the exertion to relax before increasingly becoming stretched again when it swings back towards B in the next half rotation. As we saw, the crust of the neutron star is composed of the relatively lighter electron-degenerate matter with respect to the mantle being composed of heavier neutron-degenerate matter. Because of the gravitational shearing forces arising from the aforementioned kinematics exerted upon each of the two neutron stars, this lighter crust is effectively torn off and vaporized in the process, becoming a diffuse electron-degenerate cloud of plasma surrounding the doomed neutron stars. This vaporization of the crust, in turn, releases the atomic nuclei entrapped within it, thus allowing them to escape. Coupled to this, free neutrons are also released in this stripping of the crust, which in turn slam into the escaping atomic nuclei. This collision and absorption of free neutrons by atomic nuclei generates the rapid neutron capture process, the R process, by which heavy elements are forged. It is from this R process that we see the atomic nuclei being transformed into the rare heavy elements such as gold or platinum. The violent explosion of the Kilonova event itself in turn casts these elements out into the wider universe. Thus the gold inside our universe is formed in the heart of a kilonova, which is then scattered out into the universe in the merger and collision of two neutron stars. Hence, this is the reason why I use the term philosopher's stone, because that literally is what happens as base metals are transmuted to gold here by the R process. The gold found on Earth is evidence that a neutron star merger occurred in the planetary nebula that gave birth to our solar system, and it is this process that leads me to the causal reason that gives rise to my prediction. In presenting the Big Bang kilonova hypothesis, I describe how the birth of a rotational black hole in turn gives birth to a rotational white hole on the other side of the entrapped wormhole. This in turn inflates two new entrapped manifolds of spacetime, which, like balloons, inflate forth from the polar regions of said newly born black hole. Some, or more than likely most, of the vaporized crust will be entrapped inside the event horizon of the black hole being born. The black hole and its event horizon are born because of the cumulative weight of two neutron stars in such close proximity. As the vaporized crust is also in close proximity, it will be entrapped inside the event horizon or fall into it, and thus its only path of travel is down through the wormhole to be ejected out into either of the two smaller scaled realities of the newly born universes. Fractal geometry is the cosmological principle, and thus self-similar patterns happen irrespective of scale. So given that the scale of the superverse is so much larger, where a single star's diameter is 330 million light-years, such as the one in the Boite supervoid, then what would such an atomic nuclei of the superverse be like in our universe? The answer I am led to believe is that such an atomic nuclei of the superverse is to us a supermassive black hole. Thus, these superatomic nuclei, the gold nuclei of the superverse, are to us the supermassive black holes we find in the center of galaxies, meaning, by applying the story of the Philosopher's Stone and our cosmological principle, I have an origin story for how supermassive black holes came into our universe in the moments preceding the Big Bang Kilonova event itself. It is because these seeds of galaxy formation are inside the resultant ball of hot plasma that is our early universe, from around which galaxies are formed, that therefore leads me to make the prediction that the James Webb Telescope will be able to see spiral galaxy formations all the way back to the time of the last scattering of the cosmic microwave sky, some 300,000 years after the Big Bang event itself. Effectively, these supermassive black holes will feed upon the surrounding plasma that is the very early universe. This will lead to the formation of accretion disks, which in turn grow, becoming quasars in the process as these supermassive black holes feed. The size of this accretion disk will also grow because of the expansion of the early universe, and this in turn leads to the formation of proto-spiral galaxies. The feeding black hole in turn gives birth to a pair of subverses that, like balloons, inflate forth from the polar regions of said black hole. The inflation of these subverses, coupled with the rotation of the accretion disk and the expansion of the early universe, give rise to the spiral galaxy shape. The inflation of the subverses in turn form a halo around the galaxy. These subverses, being entrapped manifolds of spacetime within our own universe, in turn become to us dark matter, the matter in them being entrapped. As the two subvertices inflate, they come to occupy the polar regions, to the north and south poles of the given supermassive black hole. In effect, as they grow and expand, both from being inflated by the associated white hole and from the expansion of the early universe itself, these subvertices come to form a halo formation which surrounds the entire spiral galaxy as a whole. Hence, I expect to see spiral galaxy formations to be seen all the way back to the time of the last scattering of the microwave sky. In fact, I would say 63% of the early universe was consumed by these supermassive black holes in the first 300,000 years, given WMAP shows that by that time, that 63% of our universe was composed of dark matter. In opposition to this is the Lambda-CDM model, which first has to account for the birth and formation of supermassive black holes. Then, in combination with this, it has to reckon with the creation of spiral galaxies from the initially homogeneous ball of hot plasma that was the early universe. This process is reckoned to take around 1 billion years or more. So here I am able to make a specific prediction that separates my hypothesis from the Lambda-CDM predictions. This prediction will now undergo the full scientific test in the coming decades as the James Webb Telescope carries out its mission. Though the Lambda-CDM model, I am afraid, is going to fail this test if the early data is verified. Already, papers such as Panic at the Disks, followed by articles claiming the Big Bang didn't happen, are already causing, well, panic. I, on the other hand, don't panic. Maybe I should play some disaster area in the background while doing our deep dive. And not even before I am able to make this film, the James Webb Telescope has identified at least 6 massive supercompact galaxies dating to around 570 to 700 million years after the Big Bang event itself, the confirmation and the discovery of which has made headlines all over the mainstream media. For the Lambda-CDM model predicts that it would take at least 2 to 3 billion years for such massive galaxies comparable in size to our own Milky Way galaxy to have formed. Yet in these 6 galaxies captured by the James Webb Telescope, we see the formation of structured spiral galaxies with around 100 billion stars existing some 600 million years after the Big Bang event. On the other hand, as I stated at the beginning of this film, I made this very specific prediction as a means of testing my hypothesis. So what can I say? Called it. As a note, Eric Lerner, who wrote the Big Bang Didn't Happen article, is a supporter of the plasma universe model proposed by Hans Alfvén. My primary contention with this model, particularly as presented by the Thunderbolt of the Gods project, is that they seem to ignore evidence such as redshift and the existence of black holes in order to still make their model work. They have their reasons, but it is an old, dying cosmological model dating from the 1970s. One reason is that they make the argument that the sky as seen from Earth was drastically different when man was still living in caves. The electric universe, as they call it, caused formations to appear in the heavenly sky which early man saw and drew. I will take my hat off in that they were the first physicists to try and link the sacred artwork and patterns commonly seen throughout human civilizations and history to structures and formations within the universe. I thought I was going mad at first in thinking about this idea, so it was a huge relief to find someone else saying the same. Shame they didn't follow through and actually practice the art themselves. I did, and now a few years later, I have no problem explaining the birth of our universe via a kilonova in describing concepts such as the Philosopher's Stone, hence the need for a heavy drink and a place I can go and recuperate. Mind you, given that my beard has turned white, the immortality benefits of either it or the Grail are rather misleading. It is there to show the immortal nature of the human soul, but not the physical body. An argument I am to make in another episode once I have laid enough groundwork in order to describe the internal structure of the one-electron universe. Another consequence, and the primary motivation, that leads me to making the prediction that the James Webb Telescope is going to see disk and spiral-shaped galaxies right back to the time of the last scattering is Lionel Shamier's work. Shamir looked to measuring whether there was any asymmetry in the observed clockwise spinward direction of spiral galaxies. When looking through a telescope, in order to view a spiral galaxy, you'll see the arms of said galaxy. Now you may see those spiral arms as having either a clockwise rotation or an anti-clockwise rotation. It is this binary distinction between clockwise and anti-clockwise of the arms of spiral galaxies that Shamir measured. Accumulating a dataset of around 100,000 images of different spiral galaxies taken from autonomous observatories such as the Sloan Digital Skies Survey, Shamir measured this binary distinction between clockwise and anti-clockwise spiral arms. Given a truly isotropic universe, then one would expect there to be no statistically significant difference between the number of spiral galaxies with clockwise spin versus anti-clockwise spin, and when viewed for the whole sky, this is indeed the case. But in comparing local regions of the sky to see if there was any variation symmetry in spinward direction, then Shamir found there to be statistically significant asymmetry in particular regions of the sky. Using spheric harmonic analysis, Shamir produced dipole and quadrupole maps showing the amount of asymmetry between clockwise and anti-clockwise spin. The real shocking surprise came from the pattern of the asymmetry shown in the subsequent maps of both the dipole and quadrupole. The great surprise was that the dipole and quadrupole maps of spinward asymmetry were an exact match to the dipole and quadrupole maps of the cosmic microwave background sky. When viewed one over the other, the maps showing spinward asymmetry and the maps showing temperature of the microwave sky are a match. The only reason they could possibly match is if there is a direct causal connection between the spiral direction of rotation of a given spiral galaxy and the very early universe, when it was not even more than 300,000 years old. In other words, spiral galaxies must have formed before the time of the last scattering, some 300,000 years after the Big Bang event itself. Hence, why I say Liner Shamir's work is the primary motivation that leads to this prediction, as Lambda-CDM, which like Banks is described as being too big to fail, predicts that at least 1 billion years must have passed since the birth of our universe before spiral-shaped galaxies could form, then a direct causal connection is problematic to say the very least. It is so problematic that it provides a point upon which I can show the validity of my hypothesis in making scientific prediction based upon my proposed hypothesis. Meaning, in returning back to a kilonova explosion in a superverse, the crust and its mantle of each of the two neutron stars are torn off in the moments preceding the actual collision itself. In these final few moments preceding the Big Bang itself, a number of critical things occur. Firstly, the gravitational shear of each body upon the other pulls the lighter electron-degenerate crust from the star, releasing the atomic nuclei. Being inside the superverse, these atomic nuclei will become the supermassive black holes that exist in the center of galaxies within our universe. Remember, fractal geometry is the cosmological principle, and the surrounding superverse is an exact copy of our universe, except for one of scale. Our universe directly inheriting the characteristics from our parent superverse. This atomization of the two neutron stars of the superverse upon each other envelops the surrounding region to form an accretion disk of plasma filled with free neutrons and heavy atomic nuclei. These neutrons and nuclei collide, giving rise to the alchemical rapid neutron capture process by which new heavy elements are forged. The second critical thing is a rotational black hole of the superverse is born. By born, I mean that an event horizon forms from which no matter or light can escape. It is born because of the additive mass-energy density of the two neutron stars being in such close proximity to each other. In providing a fuller description, I extrapolate upon the Kerr solution of the rotational black hole, but more specifically, it is in considering Nikodem Popolonsky's work and his use of an Einstein-Cartan formulation that I lean towards. The reason being that an Einstein-Cartan formulation of general relativity, which accounts for torsion, stops the ringularity from collapsing to a ring of infinite curvature. Rather, the ringularity, I feel, is an even more collapsed form of degenerate matter, which is held up by the degenerate pressure arising from the torsion tensor. In effect, I wonder if the two neutron stars really collide, as the matter in them undergoes total gravitational collapse, meaning that the gravitational shear upon the other deforms each of the two stars as we discussed. The shear upon each stretches each other out, following the spiraling circular orbit, each stripping the other of its mantle and outer core, exposing the quark-gluon plasma inside. Effectively, the two stars deform until they merge together, forming a single ring, which itself collapses down into becoming the singularity at the heart of the newly born black hole. Though, on reflection, I do think there is an actual point of physical collision between the two superneutron stars, and the Kilonova event itself really begins. The imprint of this impact and the resultant matter that came to form our universe is seen in the large-scale anisotropies of the microwave sky. Another important point in regards to Nikodem Pompolanski's work is that his cosmological model describing how a black hole can give birth to a new universe can be expressed in terms of the critical FLWR metric. The Kerr metric is a local solution of general relativity in that it is used to describe the gravitational spacetime curvature of one or more astrophysical bodies, like a solar system for example. The FLWR metric is a cosmological solution of general relativity that is used in the Lambda-CDM model in order to describe the entire universe as a whole. Pompolanski showed that there exists a one-to-one mapping between the interior of a rotational black hole and the FLWR metric, thus providing mathematical justification to the idea that our universe was born forth from a rotational black hole. The Kilonova event begins. The collision between the two neutron stars occurs, shattering each of their bodies apart. The resultant explosion outwards in a heartbeat turns inwards towards the center as the fabric of the superverse is ripped apart. The fragmented mass of the two stars spins into forming an accretion disk whose state of matter is beyond our current best descriptions. The neutron degenerate material undergoes further collapse and the singularity is born. Along with the singularity, an entrapped wormhole forms, sucking matter down into its gaping vortex. The very fabric of the superverse, its electromagnetic field, is torn in two by the wormhole, such that the two new balloon manifolds of entrapped spacetime are born and inflated forth from the rotational white hole on the other side of the entrapped wormhole. One entrapped balloon manifold of spacetime being our universe, the other being our parallel universe of antimatter. The third critical thing happening in the Big Bang Kilonova event is the production of gravitational waves across the space-time fabric of the superverse. Just like the merger of two neutron stars in our universe, a Kilonova event in the superverse causes spiral waves to ripple out across the space-time fabric of the superverse. As the two stars spiral closer to one another, the greater in both magnitude and frequency do these waves become. Then after collision, only once the event is over do we see the source of these waves become one and they die out. Once the source has ceased, the remaining gravitational waves ripple on out across the fabric of the superverse. Ultimately, our universe, along with our parallel twin, are born from the electromagnetic field of the superverse, being ripped apart and throttled through the wormhole, leading to the expanding space-time manifolds which, like a balloon, inflates. One of those balloons being our universe. However, to fully communicate my vision of this and why is the recurrent theme of all my work. But what is the shape of the newly born universes as they are being inflated? To see this, we look to the cosmic microwave background sky in the lower dipoles. Spherical harmonics upon a spherical surface is equivalent to using a Fourier transform upon a flat surface. the Fourier transform function being that function which converts the waveform of a signal as a whole into the various frequency components that make up the signal. This form of analysis is best understood in terms of standing waves upon a vibrating string. When flicked, like a guitar string, a waveform can be made to travel down the length of a rope before it is reflected back in the other direction. This is a transverse wave. However, if the rope or string is vibrated at a specific frequency, a standing wave forms. The first standing wave that forms is a single crescent waveform. It is the waveform produced when skipping a rope and is known as the first harmonic. If we now double the frequency of vibration, going up an octave, we are then able to form two standing waves, forming a full wave crest. This is the second harmonic. Double the frequency, up an octave, and we get four standing waves. The third harmonic. Again, double the frequency, and we get 8 standing waves. The fourth harmonic. Each time we move up the scale by an octave, doubling the frequency results in doubling the number of standing waves. It is this doubling, expressed as 2 to the power n, where n is the given harmonic, we see employed in the multipole expansion of the CMB. The dipole is the first harmonic, expressed as L equals 1, where di means 2. The quadrupole is the second harmonic, expressed as L equals 2, where quad means 4. 2 to the power of 2 equals 4. The octupole is the third harmonic, expressed as L equals 3, where octu means 8. 2 to the power of 3 equals 8. The hexadecapole is the fourth harmonic, expressed as L equals 4, where hexadeca, as in hexadecimal, means 16. 2 to the power of 4 equals 16. What this form of analysis does is identify the standing waves that formed within the plasma of the very early universe. The idea is that fluctuations occurred within the expanding ball of plasma that was the early universe. Standing waves would then subsequently form within this plasma, arising from the shape and fluctuations of the early universe. This in turn would lead to areas of higher and lower density, which in turn is related to the temperature of the microwave sky. The hotter an area, the greater the concentration of mass energy density. Vice versa, areas with less mass energy density in turn are colder. Hence maps of the CMB, which show temperature variation, translates into being a map of the mass energy density of the early observable universe. To see this, we first look at the CMB dipole map. Now, a large body, if not the majority of cosmologists, think that temperature variations in the dipole map is due to a Doppler shift effect arising from Earth's passage through the universe as a whole. But from looking at the dipole map of spinward galaxy asymmetry, we have a map of a cosmic-wide phenomenon which matches the CMB dipole. Given the two maps are related to precision of greater than 6 sigma, then leads me to conclude that the CMB dipole is a result of fluctuations at the very largest scale. As a note, in my previous podcast, I presented this argument in discussing Shamir's work. In addition, and far more conclusively, having been reproduced, astronomers looked at testing the local kinematic interpretation of the CMB dipole by looking at the Doppler shift of over 1 million quasars. They discovered a similar dipole structure, similar to the CMB dipole, causing them, and I quote, to rejecting the canonical exclusively kinematic interpretation of the CMB dipole. In effect, they found that the Doppler shift of respective quasars have their own similarly shaped dipole, but not fully aligned with the cosmic microwave dipole. So, in looking at the map of the CMB dipole, the first harmonic, we see a full single waveform running through the equatorial of the map. This wave formation is a single standing wave whose full shape is equal to a single complete waveform. From this, we know there are wave fluctuations within the hot plasma of the early universe, but what we don't know is what the frequencies of those standing waves are. We do know that the wavelength of the wave, or rather waves plural, is smaller than or equal to the length of the observable universe, or rather, the spherical volume within the much smaller, hotter and denser universe that went on to expand into the spherical volume of space that is to us our observable universe. However, we must be very careful in comparing the CMB dipole to the quadrupole and octupole maps. For one, the alignment is orthogonal to the CMB dipole, and secondly, the temperature variation compared to all the subsequent higher pole maps is 18 times greater, meaning of all the temperature variations, the CMB dipole is the greatest. So how do we make sense of this? Asks the Cheshire Cat. Well, by my hypothesis, the flow of matter into our universe through the ringularity is in one direction, and one direction alone. If it was going in the other direction, then that matter would be antimatter entering our parallel universe of antimatter. Further, when our universe expands, it is constrained by both the symmetrical expansion of our twin and the speed limit of the superverse. This ensures that the entire universe is moving through the superverse in the opposite direction to our CPT symmetrical twin verse. As our entire universe is moving in the same direction, us with it, we get this temperature CMB dipole variation, which is not even discussed by theoretical cosmologists. In addition, in my essay about the cold spot upon the CMB, I made the argument that the universe is expanding in the same general direction, which resulted in a space opening up between the white hole and the rest of the universe, giving rise to the formation of the Eridanus supervoid. Notice that both the cold hemisphere of the CMB dipole and the cold spot both lie down in the Eridanus region of the southern night sky, meaning we know exactly where our universe was born inside the superverse and in which direction it is expanding. Looking at the CMB quadrupole map, the second harmonic, we see two full waveforms running through the equatorial line. Like the first harmonic, this tells us that the frequency of the standing waves, plural now as there are two full waveforms, whose wavelength is smaller than or equal to the length of half of the observable universe. It is when we get to the CMB octupole map, the third harmonic, we see three full waveforms running through the equatorial line. Now, in the first and second harmonics, the wavelength of the standing wave is equal to that of the given harmonic. The first harmonic waveform matches the waveform identified on the CMB dipole map. The second harmonic matches the waveform identified on the CMB quadrupole map. The third harmonic, however, does not match the waveform identified on the CMB octupole map. As if it were, we would see four full waveforms. However, we see three full standing waveforms, which means that in the octupole map, we finally get to see the full standing waveform and their exact wavelength. That wavelength being 1/3 the size of our observable universe. When we look at the CMB map of the fourth harmonic, we now begin to see other standing wave formations that are not spread out across the entire universe. Then we have the fifth harmonic, which has a rather interesting cubic lattice wave formation covering the entire universe. This particular harmonic intrigues me, as I think this possibly could be the signature of the cubic isometric crystal lattice from which our homogeneous and isotropic universe was born. Then, in the sixth harmonic waveform, we have 6 standing wave formations, which I believe is the second harmonic of the waves seen in the octuple map. The reverberation of the initial 3 standing waves within the primordial plasma produces waves double in frequency, creating a wave formation that has 6 standing waves. The initial 3 waves we see in the L=3 octuple map. The 6 standing waves we see in the L=6 map of the CMB. Seeing this adds to my conviction that the 3 standing waves are a real formation in the early universe, because in turn we see 6 standing waves in the second harmonic, just as we see both a first and second harmonic waveform when playing a note on a piano. After a fashion, what we are doing as we move up through the harmonics in our analysis is effectively like tuning a radio in increments. With each change in station, we move up an octave, looking for those waves whose frequency is within the given octave we have moved up to. In a nutshell, a mission like WMAP, which runs over a number of years, continuously measures the cosmic microwave background from all spherical directions. The higher the harmonic number is, the higher the frequency, hence resolution and detail of the map. But in order to create such high resolution maps, we need millions or billions of data samples. So by taking microwave background measurements in the depths of space, WMAP and Planck collect enough data to produce maps of higher and higher resolution and detail. However, the standard model of cosmology, the Lambda-CDM model, says that the universe is both homogeneous and isotropic at scales which are sufficiently large, over 250 million light years, meaning that the formation of standing waves larger than this is problematic, to say the very least. And if you were to ask such questions, don't expect to have any career progress as a professional cosmologist. Just saying, while I go about nuking the entire field single-handedly from orbit, from my point of view, priests of a science are not real physicists, at which point World War III actually begins as the physics departments from every university go into full jihad mode. But we'll talk about the Grail before the end. For the moment, let us consider 2 alternative hypotheses that could account for such large-scale features in the context of the Big Bang Kilonova hypothesis. But in order to talk about them, we must understand the problem that has led cosmologists to be in this situation. The problem is that the universe looks exactly the same, operating under the same laws of physics as every other place in the observable universe. Pointing our telescope, we look at 2 regions, each at the edge of our observable universe, where said regions are at the polar opposite ends of the universe from each other. So effectively, if we were to look at 2 regions that have been separated since the very moment of the Big Bang by the expansion of space-time, that expanse being over 80 billion light years in length, then we are looking at 2 regions that have been causally disconnected from each other since the moment of creation. What we see in these 2 causally disconnected regions is that they have spiral and elliptical galaxies populated by stars whose spectra contains atoms from the periodic table. In other words, they are the same, operating under the same laws of physics. So, according to the Lambda-CDM model, the universe was born from a single point of infinite density and curvature, the singularity. This point of infinite density, for whatever reason, began to expand and inflate, going from infinitely small to an ever-expanding ball of hot plasma. This is the classic telling of the Big Bang Theory. The problem in this explanation is that in order to produce a homogeneous and isotropic universe, such a perfect ordering had to be preserved in the very milliseconds preceding the start of this expansion. Then, added to this, is the constraint that the expansion must have spherical symmetry. Such is the import that George Lemaitre, the father of the Big Bang Theory, spends the first chapter of his book, The Primeval Atom, covering both the geometric and philosophical history dating from the time of Archimedes as to why spherical symmetry is a fundamental ingredient of the Big Bang Theory. But to quote from the chapter summary in the introduction, to quote, "The first chapter deals with the theory of non-static fields having spherical symmetry, which is required to establish Friedmann's equations in the second chapter." End quote. The cosmological metric, the FLWR metric, is named after Friedmann, Lemaitre, Robertson, and Walker. And here we have Lemaitre spending the first chapter of his book dedicated to the importance of spherical symmetry, as it is a requirement in deriving Friedmann's equations, which he then goes on to do in the second chapter. For me, as a cosmologist, I consider Lemaitre's book, The Primeval Atom, to be equivalent to as how Charles Darwin's On the Origin of Species is to evolutionary biologists. To all ideas, there is a beginning, and as we've just seen, a neutron star is Lemaitre's primeval atom. The precision required, in line with the second law of thermodynamics, that such an expanding hot ball of plasma could grow with such perfect order while simultaneously holding perfect spherical symmetry is 1 in 10 billion to the power of 123, to quote Roger Penrose in discussing the tuning of fine constants. The fact that the odds are so improbable are seen by many as proof of a single divine creator, more commonly called the anthropic principle. Knowing personally the one who taught me but is not, let me now show you what true improbability looks like when Handel said a divine creator is actually in play. Have you ever heard the phrase bouncing off the walls in excitement? That's me every day. Well, it's more staring into the distance as glory of my conquests build up. One such trophy now is the optical observation of AT 2017 GFO, the binary neutron star merger whose tale we told earlier, has been observed to have near perfect spherical symmetry. This completely took everyone by surprise. Well, I had my explanation down in about 10 minutes, followed by doing the artwork and giving vision to said explanation showing the expansion of our early universe, along with our twin, from the godlike point of view, God being a native life form evolved from the superverse, and thus able to be an observer inside the superverse, causally connected to it. Then, recursively, I apply the same pattern in creating this artwork showing the feeding supermassive black holes in the quark-gluon plasma of the early universe, leading to the formation of spiral galaxies surrounded by dark matter halos. By studying the evolution of the spectral light of the AT 2017 GFO Kilonova event, Sneppen and his colleagues identified the expected strontium ion signature coming from the gaseous expulsion given off by the actual kilonova itself. By studying the evolution of the light, taken over the course of several weeks as the nova fades, astronomers are able to build up a velocity profile both in the horizontal and vertical that allows them to see the resultant shape of the newly born nebula. Because of the twin kinematics arising from the collision of two neutron stars, everyone expected an asymmetrical explosion. So the discovery that the strontium ions, whose P Cygni spectral profile from the observed light showed a spherically symmetrical explosion, was a complete shock to everyone. In addition, a shape analysis of the spectral lines also, and independently, confirms that the AT 2017 GFO kilonova between two neutron stars is in fact symmetrically spherical from the very start. To quote the abstract, we conclude that energy injection by radioactive decay is insufficient to make the ejector spherical. A magnetar wind or jet from the black hole disk could inject enough energy to induce a more spherical distribution in the overall ejector. However, an additional process seems necessary to make the element distribution uniform. End quote. Grinning, the Cheshire Cat asks, so what is that additional process? The superverse has its own speed of light limit across its electromagnetic field, but the local field caught in the middle of the singularity as it forms is also entrapped. The flow of spacetime from the superverse down into the singularity and then around it and back up is going faster than the speed of superlight, photons of the superverse. Of course, whether the speed of a superphoton is equal to the speed of photons across our electromagnetic field does become the question. But operating by the same rules of relativity, the superverse has a speed limit by the law of self-similarity. So what happens when two entrapped manifolds of spacetime are being inflated with a quark-gluon plasma, be it in the superverse or AT 2017 GFO, where that speed limit is being exceeded by the matter being ejected in from the associated white hole? Well, the entrapped manifolds expand in all directions in equal measure, constrained by a given versus speed of light. The additional process that is not accounted for is the birth and expansion of a pair of subvertices, whose expansion is driven by the expulsion of the quark-gluon plasma from the white hole and into the two entrapped manifolds of spacetime that are newly born twin pair of vertices inside our own universe, hence the name subverse. As the flow of spacetime below the event horizon of the newly born black hole is faster than the speed of light, then causes me to say that the rate of this expulsion from the white hole is faster than the speed of light. However, special relativity forbids this faster than light expansion, and thus the explosion and expansion of the subvertices is constrained, thus rendering answer to the exact how and why our universe had spherical symmetry, which in turn led to the homogeneous and isotropic expulsion and distribution of matter in the very early epoch of existence. Then, as we follow through, I apply the same logic to the evolution of early galaxies in that their supermassive black holes feed, giving rise to the same kinematic pattern that is the very fractal of creation. And as for God, he was doing a massive number on my head for one. I could tell you some tales that would turn your hair white. Like the time I went and did a vlog about what my underlying spiritual beliefs and my reasoned argument for God in the context of Darwin's theory of evolution. And in the middle of taking a break between recording it, I happened to see a series of extremely important papers in regards to Doppler comparisons between the CMB Dipole and quasar groups, the vlog of which I did the very next day and of which we previously have just discussed. Though, in answering my previous question, what is the speed of a superphoton, I lean into the fact that general relativity tells us that knowledge and information move across the gravitational field at the speed of light. If the sun were to suddenly vanish, we would only learn about it 8 minutes later. However, a photon is of the omnipresent electromagnetic field, and superphoton a particle of the superverse's electromagnetic field, ripped and inside to us the gravitational field, where we find both have the same speed limit, namely the speed of light. Returning back now to the alternative hypothesis, namely inflation theory and the standard model of cosmology, I now officially name my bitch. The mistake was to come at the creation problem from a purely quantum perspective and relegate general relativity to one of scale, when the Kerr metric describes what happens to scale. The quantum version of inflation by the unprovable decay of the inflationary field, which invents matter from nothing, is responsible for quantum fluctuations in the very early universe. Seriously, can theological cosmologists from around the world hear yourselves talking about matter from nothing? Theoretical cosmology, well, I do both in spades, holding my trophy high, which really turned my beard white. The quantum theory of inflation is in effect a mathematical symphony that answers many of the underlying problems facing cosmologists back in the 70s and 80s. It describes the faster-than-light growth of an infinitely dense point, the singularity, that grows as a perfectly homogeneous and isotropic spherical volume from infinitely small to about the size of a pea. In this perfect ordering of everything, both matter and antimatter are created in near equal measure. Well, I say near, because for every billion particles of antimatter, there are 1,000,000,001 particles of matter, and we say that because of the kaon particle only. It is this 1 out of 1,000,000,000 that manages to survive the resultant annihilation that then goes on to form all the matter in the universe, all the while maintaining the perfect order of being homogeneous and isotropic as it undergoes inflation. Given that our universe exists as we see it homogeneous and isotropic, coupled with the fact that relativity and scale invariance tells us that the superverse has a speed limit and that a kilonova has an observed symmetrically spherical explosion, is my best argument for the existence of the superverse. Fractal geometry is the cosmological principle, and the whole is found by studying the pattern inside. That pattern, a kilonova. Dark energy, that mass energy belonging to the temporary separated, but not spatially separated, surrounding superverse, is proof of this true colossus of scale. In turn, it gives a causal reason as to exactly how and why our early universe was able to expand with spherical symmetry as it is being fed with the quark-gluon plasma which came from the superverses, most homogeneous and isotropic form of matter, two superneutron stars. How two superneutron stars, or just neutron stars, come to be in such close proximity has proven to be a bit of a mystery. A core collapse supernova large enough to give birth to a neutron star was thought to be of such magnitude that the orbit of any nearby binary partner star would blow said partner away from it. However, as core collapse supernova giving birth to a neutron star as opposed to a hypernova which gives birth to a black hole, there is no birth of a pair of subvertices. Whereas, for the exact same reason as just given, I predict that such hypernovae should also have spherical symmetry. But when giving birth to a neutron star, the explosion is asymmetrical, or rather bipolar, aligned in the direction of the gamma ray burst. Thus, such a core collapse supernova explosion and birth of a neutron star produces a shaped charge whose direction is orientated with the dying star's axis of rotation, which is most likely orthogonal to the orbital plane it has with its stellar partner, meaning the resultant supernova does not blow the other star away. Or, that is my thinking, having only just learnt about the identification and the dynamics of such a system found in our own Milky Way galaxy, 11,000 light years from us, having just recorded the previous paragraphs. You kind of get used to it after a while. Highly improbable events being called in from heaven that are danger close, provoking a very human reaction.
I know it's real.
But it can't be said that such higher powers are not without a wicked sense of humour, loving to play April Fool's jokes, having just learnt a new word. That word being blitzar. A blitzar is, to quote Wikipedia, a hypothetical type of neutron star, specifically pulsars, that can rapidly collapse into black holes if their spinning slows down. Heiner Folke and Luciana Rezzola proposed these stars in 2013 as an explanation for fast radio bursts. So a blitzar is the proposed name of the object which this film has literally been discussing. Though this work is in relation to finding a source and explanation for highly polarized fast radio bursts, the direct observational evidence linking a known binary neutron star merger using LIGO's gravitational wave orrery and fast radio bursts was published in Nature a couple of days ago. Though it is the, to quote, spinning slows down in the blitzar's definition that has my attention, coupled with the question, but what if the spinning doesn't slow down or is unstable? The subject of which will most likely be the central focus of my next film in talking about pair instability supernovae and boats, brightest of all time. Yet another highly improbable event from 2 billion light years away that literally affected the entire Earth's atmosphere, which happens to, quote, 1 in 10,000 years. Kilonova research is certainly the most divinely active field of research in all of science, particularly when your evolution and immortality as an ecosystem of souls depends on it as a matter of survival. But to be honest, the whole experience of this at times just gives me the
screaming heebie-jeebies, you know what I mean.
In creating vision of said hypothesis, we have just seen why the universe is homogeneous and isotropic. But in terms of explaining the large-scale anisotropies seen in both the lower multiple CMB maps and then in the final high-resolution map, I have two competing theories. The first hypothesis is born of the final shape seen in the high-resolution map. Namely, we see two spiral arms, one hot and one cold, in the southern hemisphere. The epicenter of the spiral arms are two adjacent spots, a hot spot and the cold spot, or rather CMB cold spot as it is known, of which I explain in my essay of that title. It was seeing this twin spiral armed pattern that forced me to go from using a hypernova as my explanation to using a kilonova, as this matched the pattern of how gravitational waves form inside a kilonova. I changed my hypothesis from being the Big Bang hypernova hypothesis to the Big Bang kilonova hypothesis. So as the two superneutron stars of the superverse, like neutron stars inside our universe, as they spiral in towards one another, they emit gravitational waves that ripple out across the fabric of the superverse. The shape of these waves forms a double helical spiral in whose epicenter are the two stars spiraling in towards one another. As the two stars spiral in closer, both the magnitude and frequency of these waves continues to increase. Then, at the point of collision, the largest wave is emitted, after which the magnitude of the wave decreases exponentially. As the ringularity and its associated black hole are born, the space-time fabric of the superverse within the ringularity center becomes entrapped. The entrapped fabric of the superverse's electromagnetic field inside the ringularity begins to inflate and expand, being driven by the flow of space-time from the superverse down into the ringularity and then back up and out via the newly born white hole. Coupled to this, the quark-gluon plasma and atomized mass of the two neutron stars in turn falls into and through the ringularity such that it becomes entrapped inside our newly born universe, the pressure from which also drives the process of inflation. As noted, the rate at which our universe can expand is restricted by the superverse's speed of light limit, just as the rate of expansion of a subverse born from a kilonova inside our universe is restricted by the speed of light, as nothing can travel faster than light. Now, the main vector of travel and force of the matter being ejected via the white hole, located in the polar region, is unidirectional along the axis of rotation away from the newly born black hole. The resultant signature of this single direction of travel through the ringularity and into our newly born universe is seen in the CMB dipole. The simple fact is that us, along with the rest of the universe, is moving in the same general direction, and this is seen both globally in the CMB dipole, then seen when comparing the Doppler shift of quasar groups, and more locally in how our local galaxy cluster, the local group, flows around the volume of the local void towards the shapely supercluster, an idea formerly known as dark flow. Now, as the flow of spacetime into the black hole is equal to the speed of light at the event horizon by definition, and superluminal below said horizon, when extrapolated, leads me to say that the matter being ejected via the white hole is moving faster than the speed of light. However, this faster than light ejection of matter is constrained by the supervertice's speed of light limit. Because the rate of expansion is constrained, the primary unidirectional flow of plasma fans out such that it pushes equally in all directions against the entrapped surface. Thus, the rate of inflation in the initial epoch of our universe is constrained by the supervertice's speed of light limit, thus giving rise to a spherically symmetrical expansion. Now, as noted by George Lemaitre, spherical symmetry is a fundamental requirement for the development of Friedmann's equations describing an expanding universe. Because the rate of expansion is constrained by the speed limit of the superverse, we have answer to how this requirement of spherical symmetry is fulfilled. In turn, we can apply the exact same argument to a pair of subvertices being born inside our universe in order to explain the unexpected symmetrically spherical expansion of the observed binary neutron star merger ATF 2017 G. But we should note that there are two entrapped surfaces of spacetime that inflate forth from the newly born rotational black hole, meaning that one entrapped manifold inflates from the North Pole and its parallel opposite inflates from the South Pole. The spherical expansion of each of the newly born vertices downwards causes the accretion disk to become sandwiched in between the two of them. Like pushing two balloons together, the two vertices equally repel one another, which further constrains the expansion of each by the other. Within the plasma of each verse, the atomized superneutron star matter transmutes into becoming the supermassive black holes of that verse, which in turn begin to feed. The exact same fractal pattern of creation is seen in the spherical expansion of the subvertices born from the supermassive black holes, as each of the two vertices push down and in towards each other. The initially homogeneous plasma is sandwiched into forming a quasar accretion disk, which will cool down into forming spiral galaxies surrounded by dark matter halos. But with respect to a kilonova, and the Big Bang kilonova specifically, the shape of the supervertices space-time fabric around the accretion disk has been warped by the aforementioned gravitational waves. So as our universe expands outwards and downwards onto the accretion disk, it follows the curvature of the gravitational waves. The phase of each of the gravitational waves are polar opposite with respect to each other. The phase of the blue gravitational wave is in the upwards direction, such that the wave forms a crest above the plane of the equatorial. The downward expansion of our universe onto this wave crest, indents the shape of our universe, pushing its surface upwards. As the crescent wave impinges itself onto the shape of our universe, it pushes matter away from it. In inverse, the phase of the red gravitational wave is in the downwards direction, such that the wave forms a trough below the plane of the equatorial. The downward expansion of our universe into this wave trough allows our universe to expand into the volume of the gravitational wave. The creation of this additional volume sweeps the surrounding plasma up and into the wave trough. Thus, the red gravitational wave's trough collects matter, and in symmetrical opposition, the blue gravitational wave pushes matter away from its crescent. As our universe expands from this initial epoch, the pressure driving it lessens as the quark-gluon plasma cools down into forming protons and neutrons. This lessening of the pressure and the ever-decreasing density of the now ionized plasma of our early universe means the rate and force of expansion has slowed down, such that the constraint from the supervertice's speed of light limit is not so much applicable. As this spherical constriction of this constraint falls, the repulsion of our universe upwards and away from our parallel twin verse of entrapped antimatter begins. Again, as seen by the CMB dipole, the main flow of expansion of our universe is a single unidirectional trajectory along the black hole's axis of rotation. As our universe rebounds up and away, the curvature of our universe following the two gravitational waves then flattens back out. As matter was forced away from the formation of the wave crescent, then the region of the universe in which this crescent formed has a lower mass energy density concentration, and thus we get a cold spiral upon the final high resolution map of the CMB. Vice versa, as matter filled up the wave trough, it thus leads to a higher concentration of mass energy density in this volume when it becomes flattened out. This higher concentration of mass energy density in turn translates into the formation of a hot spiral upon the final high resolution map of the CMB. Now, the reason for saying that the indentation of the gravitational waves upon our universe flattens out is because the curvature of spacetime within the superverse is mostly flat. For the exact same reason as we have curvature of spacetime inside our universe being caused by the concentration of mass energy density, and without it, space is flat. Thus implies, by the law of scale invariance, that the shape of the supervertice's vacuum is also flat. As our universe is expanding into the vacuum of the superverse, which is flat, gives rise to the fact that we see a flat universe when measuring its curvature from the CMB. Of course, it is mostly flat, but it is also entrapped, creating a closed universe, of which evidence is seen in Planck's CMB data. In comparison, the presence of the CMB dipole and the CMB large-scale anisotropies, according to the Lambda-CDM model's version of inflation, is to ignore this evidence, as it goes against the religious principle that is the standing cosmological principle. Next, it creates matter from nothing because, well, quantum theory, violating the principle that energy can neither be created or destroyed. The inflation of the perfectly spherical and homogeneous and isotropic universe happens because of a theoretical quantum inflationary field, which apparently now decays, meaning we have no experimental evidence or observation of said made-up field. As for why and how spherical symmetry is maintained, no reason is given. That, and no reason is given for why the universe is homogeneous and isotropic, but rather is assumed to be the binding principle of all things. So that, in a nutshell, is my first hypothesis. But in looking at and in considering the lower multiple maps of the CMB, a second hypothesis emerges that gives rise to a way of testing hypotheses in regards to quantum gravity. In order for our entrapped manifold of spacetime to become entrapped, it had to pass through the singularity. In saying this, let us reconsider the two separate and causally disconnected regions we discussed earlier. Both regions would have had to travel through and thus been shaped by the singularity. That which is passing through the singularity is the fabric of the superverse, which is scaled down and crushed by the black hole. The greatest point of contraction is inside the bounds of the singularity, the entrapped wormhole, meaning that any large-scale structures that are seen across the entire cosmos, such as the large-scale anisotropies of the lower multiple CMB maps, could be there because of the singularity. In effect, these maps could be seen as our window into the singularity itself. It was in considering the octuple map, which shows 3 full waveforms spread out over the entire cosmos, that really caused me to consider this. In applying my hypothesis that such a formation could form because of the gravitational waves rippling out across the superverse, the shape of our universe, when viewed in cross-section, would have 3 lobes surrounded by 3 crests. Visualizing the kinematics, we start with an elastic circle, that being the cross-section of our balloon universe, and draw an equilateral triangle inside, such that its corners intersect the circumference of the circle. At the corners of the equilateral triangle, we apply equal force at the 3 points in towards the center. The resultant force at one of the points would push the surface inwards, leading to the formation of a crest surrounded by 2 saddles. The net effect of 3 inward forces would cause our elastic circle to deform into such a circular shape with 3 lobes, the required shape to produce such a waveform as seen in the octuple map. However, with gravitational waves, the number of separate waves, from what I can see, is always an even number. The harmonics of the twin spiral wave pattern that emanates from the 2 superneutron stars is even and not odd. 2 waves being in the first harmonic, 4 waves in the second harmonic, 8 waves in the third harmonic. The multiple of the waves is always an even number, but the octuple map shows 3 full waveforms, which is an odd number. My second consideration about the octuple map comes in thinking about the orientation, size, and shape of the 6 lobes. The orientation is running in a general north to south direction. Their shape and size runs almost the entire length of the universe as a whole, from north to south. Now, for reasons I have laid out in previous essays, I say that the rotational white hole that birthed our universe is to be found in the CMB cold spot. This is located down adjacent to the hotspot in the southern polar region. So putting this all together, given my gravitational wave explanation, means that at one point the entire universe was shaped by a cylindrical shaped wave formation in which 3 full waves existed. But gravitational waves come in pairs and spiral outwards. There is no spiraling or rifling in the shape of the 6 lobes of the octave map, or in the second harmonic L equals 6 map. So what could shape the entire universe as such if not gravitational waves? The one candidate is the singularity itself. Like a cloth napkin being pulled through a napkin holder, so too is our universe going to be shaped by the singularity. Given that the orientation of the lobes are perpendicular to where the newly born black hole of the superverse is located, the pattern is a fit. Meaning, if we imagine our napkin holder being a substitute for the singularity, is shaped like the outer bounds of a Borromean ring with 3 lobes, and we pull the fabric of our cloth universe through it, the shape of the cloth would be a cylindrical Borromean ring. One of the immediate appeals to a Borromean ring, or a hexagonal shaped formation, is the number 6. 6 is both a multiple of 2 and 3. Electrons, protons, and neutrons, known collectively as fermions, all have spin of a half, 1 divided by 2. Protons and neutrons are composed of quarks with spins of 1/3, 1 divided by 3, or 2/3, 2 divided by 3. The least common denominator of both 2 and 3 is 6. So in describing the genesis of particles, the number 6 is extremely important in describing how they got their intrinsic angular momentum. In considering the singularity itself, we know it has rotation. If it had no rotation, then the singularity would be a point singularity. Another consideration comes in how one could describe a rotational black hole as being a vortex of irrotational flow. In fact, vortices in fluid simulations are used as an analog model in order to understand the mechanics of rotational black holes. It is this mechanics of concentric irrotational flow, such as seen in the south pole of Saturn, that I first pointed to as being inspiration for understanding for the formation of our universe. The hexagonal storm of Saturn being a cross-section through our balloon manifold we call our universe. Again, remember fractal geometry is the cosmological principle, and thus that pattern is repeated irrespective of scale, even if it be the storm system on a gaseous planet which reveals that pattern. But the singularity is a place of near infinite curvature where only quantum mechanics gives description to the irrotational flow. As we discussed in considering the inner core of a neutron star, we saw the pattern formed by irrotational quantum flow. Specifically, we saw the quantum vortices arranged in a hexagonal lattice formation, where each vortex occupies a separate node on said lattice. We saw how such quantum vortices are believed to power the field strength seen inside magnetars. We discussed how such a quantum vortex may cause hotspots to appear on the event horizon of black holes, leading to testable hypotheses about the nature of the singularity. To this, I will add my top card in my pack, Martin Tajmir's experiment showing frame dragging coming from the rotation of liquid helium, meaning I have an experiment showing the generation of artificial gravity in a manner similar to how electricity is generated by a dynamo. This experiment is based around the formation of irrotational quantum flow within the liquid helium, which, as we've seen, naturally forms a hexagonal lattice of quantum vortices. It is for all these reasons that causes me to say that the lower multiple maps of the CMB are a window into the ringularity that effectively shaped and gave birth to our universe, including its fundamental particles with half and third integer spins. Now, as usual, I initially wanted to explain only the first hypothesis about gravitational waves shaping the CMB, but in the process of writing, I yet again find just the greatest vein of knowledge to start exploring. The question ringing in my mind, did I just invent a whole new field of science? Here being the study of the ringularity. Well, that's ring law for you. With all the groundwork laid out, I can now finally present my vision. That vision showing the actual exact moment of when our universe was born and why. The whole idea of black holes being actual physical phenomenon was born from Penrose's idea of entrapped manifolds of spacetime. Essentially, an entrapped manifold of spacetime is a description of spacetime that is enclosed, meaning that photons inside the enclosed volume of spacetime are unable to escape the enclosure. The event horizon of a black hole is one such enclosure because it is defined as being the surface at which the escape velocity is the speed of light. Photons inside the event horizon will be unable to escape this enclosure because inside the black hole, the escape velocity is greater than the speed of light. As nothing travels faster than the speed of light, it implies that anything inside the black hole will never be able to escape back out into the universe. We can best visualize this process of entrapment of space-time manifolds by viewing the fabric of spacetime as a rubber sheet pulled tight. To see the curvature, we draw a regular grid upon the fabric of the sheet. When no mass is present, being in empty space, the curvature of spacetime is flat, as is the sheet with nothing on it. Putting a spherical weight on the rubber sheet pulls the elastic down and around the volume of the spherical weight. In turn, we see how the regular grid symmetrically deforms in a manner that is similar to the way mass energy density deforms the fabric of spacetime. So effectively, we have a visual analog of how the weight of a spherical astrophysical body deforms the fabric of spacetime, as described by general relativity. The heavier the weight upon the sheet, the greater the force that is exerted downwards onto the sheet. This leads to an increase in the curvature of the sheet in the downward direction. For example, a tennis ball will exert only a small amount of force downwards, deforming the sheet downwards only slightly. Replace the tennis ball with a solid ball made out of iron, which is much heavier, and the rubber sheet will be pulled down even further. As the weight of the spherical object increases, the greater the curvature becomes as the elastic sheet is pulled down more and more. Use a ball of lead of the same size, and the sheet is pulled down even further, deforming its curvature to a far greater degree. So it is with general relativity. The greater the mass of a body, the greater the curvature there is in the fabric of spacetime. Looking at our sheet and ball in cross-section, we see this curvature increase for each of our three balls: the tennis ball, the ball of iron, and the ball of lead. We now replace these balls with even heavier astrophysical bodies, starting with a white dwarf. A white dwarf is so dense, being made of electron-degenerate matter, that a sugar cube of it would weigh around 5 tons. The force downwards, coming from its extreme weight, then bends our imaginary rubber sheet downwards to such a degree that the white dwarf sits at the bottom of a rather deep trough when seen in cross-section. The required escape velocity to climb up out of this trough is large, but it is less than the speed of light, meaning a photon will take time to climb up out of this trough, orbiting the white dwarf as it goes, but it can escape the gravitational pull of the white dwarf. More extreme, we now replace the white dwarf with a neutron star. Being composed of neutron degenerate matter, where a sugar cube weighs 5 billion tons, the force exerted downwards upon the sheet creates an even deeper trough as compared to the white dwarf. This increase in the gradient of the spacetime curvature greatly increases the required escape velocity from the neutron star. However, this escape velocity is still less, but almost, the speed of light. So a photon emitted from the surface of the neutron star will take even longer to climb up out of the trough before it is able to escape. But escape it can. We now replace the neutron star with a black hole. The simplest solution of general relativity, the Schwarzschild metric, describes the most commonly known and simplest black hole, the Schwarzschild black hole. The matter in the Schwarzschild black hole is described as being crushed down to a single point where the curvature of space-time becomes infinite, the singularity. Or rather, the density of the body is so great that the neutron degenerate pressure is no longer sufficient to hold the weight of its structure up, so it undergoes total gravitational collapse down to a single point of infinite density and curvature. Placed on our rubber sheet, this point of infinite density drops downwards towards infinity. As we follow the path down in towards the infinite depth of the black hole, the greater the escape velocity will become. At some point, on our way down to infinity, we cross a point where the escape velocity is equal to the speed of light. This is the event horizon of the black hole. From this point on, nothing can escape the pull of the singularity, and we are inside the entrapped manifold of space-time that is the black hole. This critical point of no return effectively divides our rubber sheet into two areas. That area of the sheet whose surface is below the event horizon, and the rest of the sheet which is outside of the black hole's event horizon. Using a Penrose diagram, we can visualize a separation between these two surfaces of spacetime, one of which is entrapped. Specifically, the Penrose diagram shows the Schwarzschild solution where the bottom right diamond is the universe, and the triangle on the top left is the interior of the black hole itself, or the diamond is the surface of the sheet outside of the event horizon, and the triangle the surface inside of the event horizon. The genius of Penrose diagrams comes in their ability to map an infinite expanse inside a finite shape, such as the diamond. Like points on a compass, each point on the diamond points to either an infinitely far off point in space or an infinitely far off point in time, the south pointing into the infinite past and the north pointing towards the infinite future. The contours of both space and time with their tangential curve move from one infinite point at the corners to another infinite point. The contours are such that any line at 45 degrees represents a photon traveling at the speed of light. As an example, a photon emitted by the hypernova that gave birth to a black hole, which then becomes entrapped on the newly formed event horizon, begins its journey at the left-hand corner. The future light cone of the photon points in towards the black hole and its past light cone out into the universe. Entrapped on the event horizon, the photon forever traverses the event horizon, neither escaping or falling in, as it is in an infinite free fall orbit upon the event horizon. This path of travel upon the event horizon into the infinite future is plotted as a world line upon the event horizon of the Penrose diagram, which runs at 45 degrees. The point singularity forms the top line of the black hole's triangle upon the diagram, as anything trapped inside the black hole is destined to fall down and onto the singularity.